Hello viewers, this is Dr. D. Rajalakshmi, Associate Professor in Computer Science and Engineering Department, RMD Engineering College. Welcome to today's video about maximum flow problem. Before seeing about maximum flow problem, let's see about iterative improvement technique. Let's see the general principle of iterative improvement technique. Actually, iterative improvement technique starts with some feasible solution, then proceeds to improve it by repeated applications of some simple step. This step involves a small localized change yielding a feasible solution with an improved value of the objective function. When no such change improves the value of the objective function, the algorithm returns the last feasible solution as optimal and stops. These are some of the example problems can be solved using iterative improvement technique. Linear programming problem using simplex method, maximum flow problem using Ford-Fulkerson algorithm, maximum matching of graph vertices, stable marriage problem using Gale-Shapley algorithm, local search heuristics. In this video, we are going to see about maximum flow problem. What is maximum flow problem? The problem of maximizing flow of a material through a transportation network is called as maximum flow problem. Transportation network can be represented by a connected weighted digraph with n vertices and a set of edges capital E with the following properties. It contains exactly one vertex with no entering edges. This vertex is called source and assumed to be numbered 1. Then the second property is it contains exactly one vertex with no leaving edges. This vertex is called the sink and assumed to be numbered n. The weight uij of each directed edge I, j is a positive integer called the edge capacity. This number represents the upper bound on the amount of the material that can be sent from I to j through a link represented by this edge. A diagram satisfying these properties is called a flow network or simply a network. This is the example of a flow network. It contains 6 number of vertices. In that 6 vertices, the first vertex is the vertex without any entering edges. So it is called as the source vertex. Vertex number 6 does not contain any leaving edges. So this is the sink vertex. The integer numbers assigned with each and every edges represent the maximum capacity of the edges. For example, the edge between 1 and 2 contains 2. It means that the maximum number or the upper bound on the number of materials that can be sent from vertex number 1 to 2 is 2. So this is the example for flow network or transportation network. Now let's see what is a flow. Flow is an assignment of real numbers xij to edges I, j of a given network that satisfies the following conditions. The first condition is flow conservation requirement and the second condition is capacity constraint. What is flow conservation requirement? The total amount of the material entering an intermediate vertex must be equal to the total number of material leaving the vertex. This is what is called as flow conservation requirement. Next, what is capacity constraint? Capacity constraints means the amount of material that are flowing through an edge must lie between 0 and the upper capacity of that particular edge. That is 0 less than or equal to xij less than or equal to uij. Uij represents maximum capacity or otherwise upper bound or the number of materials that can be sent from the vertex I to j, where xij represents the actual flow of material that are flowing from vertex I to j. This xij must be greater than or equal to 0 and less than or equal to uij. This is what is called as capacity constraint. Now flow value and maximum flow problem. Since no material can be lost or added to by going through intermediate vertices of the network, the total number of material leaving the source must end up at the sink. The maximum flow problem is to find the flow of the largest value for the given network. Now let's see shortest augmenting path algorithm for solving maximum flow problem. Shortest augmenting path algorithm generate augmenting path with the least number of edges by breadth first search as follows. Starting at the source, perform breadth first search traversal by marking new unlabeled vertices with two labels. The first label indicates amount of additional flow that can be brought from the source to the vertex being labeled. Second label is the name of the vertex from which the vertex being labeled was reached. It can be set left undefined for the source. The source is always labeled with infinity and a null value. All other vertices are labeled as follows. If unlabeled vertex j is connected to the front vertex I of the traversal Q by a directed edge from I to j with positive unused capacity, then the remaining capacity Rij is equal to Uij minus Xij. Then vertex j is labeled with L value of the previous vertex and previous vertex, that is label of the previous vertex, that is the vertex j is labeled with Lj comma I plus, where Lj is the minimum of L value of the previous vertex and remaining capacity, whereas I plus is the index of the previous vertex with the positive sign because it is based on the forward edge. In the case of backward edge, instead of using remaining capacity, the actual flow Xij must be used, and instead of using positive symbol along with the previous vertex, we have to use the negative symbol. If the sink ends up being labeled, the current flow can be augmented by the amount indicated by the sink's first label. The augmentation of the current flow is performed along the augmenting path traced by following the vertex second labels from sink to source. The current flow quantities are increased on the forward edges and decreased on the backward edges of this path. If the sink remains unlabeled after the traversal Q becomes empty, the algorithm returns the current flow as maximum and stops. Now let's see the example problem. Maximum flow problem using shortest augmenting path algorithm. This is the given problem. This problem is containing 6 number of vertices. Vertex number 1 is the source vertex. Vertex number 6 is the sink vertex. Initially, we are starting with 0 flow. The numerator represents the current flow through the edges. So, for example, the edge between 1 and 2, the maximum capacity of the edge is 2. Current flow is 0. As of now, at present, no material is flowing from vertex number 1 to 2. Similarly, all the edges are containing value 0 for the current flow. Then we have to label all the vertices. Okay. So first of all, the source vertex must be labeled with the label infinity comma null value, and that must be inserted into the queue. Then afterwards, we have to remove the front element from the queue and have to label the adjacent vertices of the front element. Here we are removing one from the queue and we are labeling the adjacent vertices of 1, that is 2 and 4. Here both the vertices are connected with forward edges, so we have to use the remaining capacity while calculating the label. So now let's see what is the label we can give for 2. Okay, so it contains 2 labels. The second label represents the vertex from which it is receiving the material and the direction. Since vertex number 2 is receiving material from vertex number 1, it is marked as 1 plus. This plus represents the direction of the flow, that is forward direction. And the first part of the label 2. How we are getting this one is, we have to identify the minimum among the remaining capacity and L value of the previous vertex 1. L value of the previous vertex 1 is infinity, and the remaining capacity is what? 2 minus 0, which is equal to 0. We are comparing infinity and 2. Minimum value is 2. So that is what is given as the first label of the vertex 2. So it contains the label 2 and 1 plus. Similarly, we can calculate label of 4. Here the remaining capacity is 3. We are comparing remaining capacity with infinity. Since 3 is minimum, that we are taking as label for 4. And the second part of the label represents the vertex from which it is receiving material. It's receiving material from 1 only. So it is represented as 1 plus. So after labeling any vertex, it must be inserted into the queue. So we are inserting 2 into the queue as well as 4 into the queue. As of now, 1 got deleted from the queue. In the next step, the next front element 2 must be deleted from the queue. After deleting 2, the adjacent vertices of 2 must be labeled. So we are deleting 2 from the queue and we are trying to label the adjacent vertices of 2. Here 3 adjacent vertices are available for 2. One is, the first adjacent vertex is 1, but it got the label already and it is connected in the backward direction. So we need not label 1 because it got the label already. We have to label 3 and 5 only. They are not yet labeled till now. First of all, we are taking 3. Okay, it is available in the forward direction. Before labeling any vertex, we have to check whether its remaining capacity is greater than 0 as well as it is an unlabeled vertex. If both the conditions are satisfied only, that vertex can be labeled. Since 3 is not yet labeled till now and the remaining capacity is 5, which is greater than 0, we are labeling 3. So label of 3 is 2, 2 plus. How we are getting this 2? Remaining capacity 5 and L value of the previous vertex is 2. Minimum among 2 and 5 is 2. That is why we are writing 2 here. And the previous vertex is 2. It's getting material in the forward direction. That is in the same direction as that of the edge. We are putting this plus sign here. Similarly, in the same manner, we are labeling 5 also. It is getting the label 2, 2 plus. 3 and 5 are inserted into the queue. Now, next 4 we are deleting from the queue. This is the next front element. Why? Because 1 and 2 got deleted already. So, the next front element which is available in the queue is 4 only. That we are deleting. After deleting this 4, the adjacent vertices of 4 must be labeled if possible. Here, what are the adjacent vertices of 4? 1 and 3. 1 is connected in the backward direction. 3 is connected in the forward direction. But 1 and 3 got labeled already. We cannot label 1 as well as 3. So, we are deleting the next front element 3. After deleting 3, the adjacent vertices, that is unlabeled adjacent vertices of 3 can be labeled. Here 2, 4 and 6 are the adjacent vertices. 2 got the label already, 4 got the label already, but 6 is not yet labeled already. And the remaining capacity 2 minus 0 is also greater than 0. So we can label 6. What is the label we are giving here? 2, 3 plus. Okay, so this is what is the label. We have to continue this process until the sink vertex got the label, or otherwise the queue becomes empty. Here the sink vertex got the label, so we can stop the procedure. It means that we found an augmenting path. What is augmenting path? The path through which some additional materials can be sent is the augmenting path. Now we found a path. How we are reaching, what is the path? How we are reaching 6? From 3. Okay, 3 plus only the second label. So this is the last edge which is available in the path. and see the previous that is previous vertex. See the second label of 3, it is 2 plus. So the previous vertex is 2, that means what, it is receiving material from 2. So we are highlighting this edge also. And here the second label is 1 plus, that means it is receiving material from vertex number 1. So we are highlighting this edge also. So this is what is the path we are getting, 1 to 2, 2 to 3 and 3 to 6. Through this path, what is the number of material can be sent? That is L value of the sink vertex is the number of materials can be sent. What is the currently available flow? 0 only. With the currently available flow, this Ln value, that is L value of the sink vertex must be added to update the flow through this path. So we will be getting 0 plus 2 by 2, 0 plus 2 by 5 and 0 plus 2 by 2 for this particular edge. So the flow can be represented like 2 bar 2, 2 bar 5 and 2 bar 2. So in the same manner, we can repeat the procedure and we will be getting the next path, 1 to 4, 4 to 3, 3 to 2, 2 to 5 and 5 to 6. The L value of the last vertex is 1. Wherever we have forward edge, this L value can be added with the numerator of that particular edge. That is, the current flow value can be added with this L value of the sink vertex. For the backward edge, we have to decrement the current value by the L value. Okay. So in that way, it can be updated like this, 1 bar 4, 1 bar 3. Here it is a backward edge. So it can be represented as 1 bar 5. Here 1 bar 1 and 1 bar 3. So in that way, the next flow can be represented. It can be shown in the diagram. This is what is the second flow, second documenting path. Through the second path, we are sending only one material. Through the first path, we are sending 2 number of materials. As of now, we are sending 3 number of materials from the source vertex to the sink vertex. Now we are going to do the same procedure for the third iteration. When we do this one, no, after labeling 1, we are labeling the vertex number 4, but we cannot label vertex number 2 even though it is the adjacent vertex of 1, because the remaining capacity is not greater than 0, it is equal to 0. So we are trying to label only 4. What is the label we are giving here? 2, 1 plus is the label we are giving. After labeling any vertex, it must be inserted into the queue. So we are inserting it into the queue. 4 is inserted here. Now in the next step, we are removing 4 from the queue. After removing 4 from the queue, we have to label the adjacent vertices of 4. Here 1 cannot be labeled because it got the label already. 3 also cannot be labeled because the remaining capacity is equal to 0. It must be greater than 0, then only the vertex which is connected in the forward direction can be labeled, right? So this 3 cannot be labeled. We cannot insert any new vertex into the queue. Now our queue is empty. That means there is no other augmenting path available. Whatever the path we found already is the result, is the maximum flow for this particular problem. So according to this problem, the maximum flow which is possible for this for the given transportation network is 3. With this discussion, we are finishing today's session. Thank you.